Very much. Good morning, everyone. As Edfine just said, I'm from Oxford Centre for Non-Linear PDs. I'm a second-year DPhil student of John Ball, and I spent most of my time working on cholesteric liquid crystals, and more generally on how the different theories of liquid crystals are actually compete with each other and where they're useful and where they're not. So, a brief introduction to cholesterics for the people who are not so familiar. So, the usual assumed minimizer of cholesteric liquid crystals is this helical configuration where the director rotates perpendicular to a certain direction. So as you move up in Z, it rotates in the XY plane. But I've just picked out a number of pictures here of all sorts of patterns that cholesteric liquid crystals can actually form. So there's some cholesteric fingers there, there's cholesteric filaments. These two on the bottom left are blue phases, and on the bottom right is a Kano wedge experiment where liquid crystal is held between two plates which get closer together. And clearly if this helix was the end of the entire story for cholesterics, all these sort of patterns, you wouldn't get all these sort of patterns, so there's clearly more to be studied there. And so that's my main goal, is to try and understand these patterns a bit better. So I start in the ozone-Frank theory with all the usual things. We have the usual ozone-Frank energy expansion, quadratic in n and the gradients of n, and with cholesterics there's this T, which is 2 pi over the pitch, which is non-zero for cholesterics. Now, one of the starting points is I will always assume that we have the normal one constant approximation, which is often assumed for pneumatics, but sometimes, or quite often, the cholesterics, the Saddle-Splay term here, is assumed that K2 is actually minus K4 rather than K4 being 0. And that's to make the integrand be minimized by this helix. But that's sort of backwards logic to a mathematician. You should set up your minimization problem and then find out what the minimizer is, rather than set it up assuming what you know what the minimizer is. So I would always assume this. And in terms of boundary conditions, I'm co-sponsored by HP Labs. An experiment that they've done is they had a diffraction, they had liquid crystal in a cell, but rather than just flat plate and flat plate, on the bottom they had this triangular pattern with homeotropic boundary data, and this actually formed some sort of bistable device, which obviously they're very keenly interested in. And so, which has not come out particularly well, but when this diffraction grating is being used, it's in the bottom half of this picture. There's actually, it's a bit faint, but there's a periodic rolling pattern there. And so in order to try and capture this sort of pattern, the boundary conditions I've imposed are strong anchoring. So it's homeotropic on the top face, and it's a planar on the bottom face with a fixed direction E1. And I always scale the domain so that the height of the domain is Z equals 1. And so that means I only need to consider T as the variable, because the ratio D over P is normally the critical thing. D over P equals 1 is normally where the patterns sort of occur. So I scale it so that I only have to worry about T. So actually the problem that I'm looking at is this one. It's to minimize this integral functional. This is the domain, and with the boundary conditions that are on the previous slide. I also, to try and capture periodic solutions, I impose periodic data in X on Y on it. So it must be periodic with period 2L1 in X and 2L2 in Y. So now that the problem's all set up, the mathematical analysis can sort of begin. And so the first thing you go to is the Euler-Lagrange equations, but they're inherently very difficult because they're a second order, they're non-linear elliptic system of PDEs, and it's almost impossible to solve these things in general. So this here is the Lagrange multiplier from the fact that n is a unit vector. So the natural first attempt to solve this is to go for a function which depends only on the height. And if you do this and write it your functional in terms of Euler angles, theta and phi, then this is what you get. And actually the Euler-Lagrange equations simplify a lot, and phi and theta separate out. And so phi being Tz corresponds to the normal helix. The phi is the rotation in the xy plane, and theta is the rotation out of the xy plane. But theta has this, because it's a mixed boundary condition, theta can't just be 0. So theta has this implicit form here, which is very difficult to picture what it is exactly. But importantly, this theta which satisfies this and that and this phi, these form an n, which is always the global minimum of functions of one variable. And these do actually, this n also then satisfies these Euler-Lagrange equations. So it is a candidate minimizer for the entire problem. So what does theta actually look like? So here's theta for a few values of t. So on the bottom of these graphs there's the height z, and on the top is theta. So you can see as the t gets larger and larger, which is as the pitch gets shorter and shorter, theta would much rather be 0 throughout most of the cell, and then just having to match the top boundary condition in some small boundary layer at the top. So it sort of makes sense. It's trying to approximate the normal helical pattern which you'd expect. And the question is this the global minimizer of the whole problem? And the answer is sometimes yes, but we don't always, or don't know yet, in all the time. So this is something that I've proved, that if there are some small parameters, there are some constant t star, so if the pitch length is sufficiently long, i.e. t is sufficiently small, then this one variable minimizer, so things like this on the top left, so smaller t, is in fact the global minimum of the entire problem, and it's a unique global minimum. I'm not written that. Unique global minimum of the entire problem. So that's great. Large pitch lengths, it's a one variable solution. But and sort of proof of this is sort of quite nice in that. So you can actually, because of this, this equation has a very nice form. It's a very nice quadratic form. When you actually take another state m and n is the minimizer, it actually has this very nice rewriting, which is almost, you see the functional again appearing there, and then you can use some mathematical analysis to prove this nice stability result. So that's all the answers for t being small, but t being large, there are lots of more issues. One of them is cholesteric frustration, which I know has been mentioned a few times in this program. So this is, again, it's very important that k2 plus k4 is non-zero here, because this is not true. If k2 plus k4 is equal to 0, we don't have this cholesteric frustration. So there is this uniform bound on the integrand of the free energy, but nothing can actually equal this bound on any sort of three-dimensional domain, but we can get arbitrarily close. So this is sort of confusing in that it tells us there isn't necessarily a natural state for a cholesteric to be in, if we make this assumption. But that doesn't necessarily stop the minimization problem from giving us the results that we want. So a common example is the double twist cylinder. So in cylindrical coordinates, this is what the direct field is. And that's sort of a line field representation. And actually, if this structure is energetically better than the helix by an order of t squared, then by an order of t squared, but only on a radius like 1 over t. So if t is very large, you've got lots of these small cylinders which are energetically much better than the helixes. And so clearly the problem would come if you're trying to make a state out of these sort of things, in sort of placing them together with each other. But there's an issue that if you, that's how the theory of blue phases work, in that you form an array or some sort of array cubic lattice of these double twist cylinders, and there's some sort of isotropic fluid in between. And so this sort of got me thinking about the second part of my talk, which is on different theories of liquid crystals. So if you actually put two of these double twist cylinders next to each other, with the correct radius, then where they meet, one cylinder has the director pointing one way, and the other one is pointing in the exact opposite direction. And because liquid crystals have n to minus n symmetry, this shouldn't actually be a problem. So it got me thinking a little bit about the different theories. So here's three different theories. Ozone Frank with the director. I haven't put in the cholesteric terms just for ease. Ericsson adds a scalar order parameter, and constrained uniaxial Q-tensor theory, rather than using a director, uses n tensor n to do this. So, and there's a paper by John Ball and Argyll Zonescu 2 years ago. If we have a bounded simply connected domain with continuous boundary in 2 or 3 dimensions, then if we have n tensor n Sobolev function, then we can actually turn this into an m, a Sobolev function of the same regularity, which is very important. That's basically saying that we can turn a line field into a vector field with the same regularity, as long as omega has these assumptions on them. So sort of a very simple corollary of this is actually that constrained Q-tensor theory, where S is constant, is exactly the same, the minimization problem, as the normal Ozone-Frank. So actually, whereas if you looked at these problems, you might think they give very different solutions. If S is constant and omega is as it is here, then the problems are actually exactly the same, which is quite interesting. But equally, perhaps even more interesting, is if we remove the assumption that omega is simply connected, if now we remove that assumption, say omega is just a bounded domain, so that's a bounded, open, connected set, then actually the constrained Q-tensor theory and Ozone-Frank theory are equivalent, but Ozone-Frank is now set in a completely different function space. So SBV for non-mathematicians is a special bounded variation function. So they are like Sobolev functions, but they are allowed to jump across lower dimensional sets. So if your domain was two-dimensional, you're allowed to be discontinuous across lines. If your domain was three-dimensional, you can be discontinuous across planes. And this condition here means that across the discontinuity set, you're only allowed to jump from n to minus n, which should seem logical. So it's quite an interesting result. If you change the assumptions on your domain omega, you actually change the function space that you're required to use your minimization problem. And in that paper of Borland, Zarnesky, here is the example they use of a non-orientable line field. So if you tried to turn this into a vector field, there would, at some point you would come a problem because you would have arrows pointing into each other. But with bounded variation functions, you can imagine, if you like, taking two cuts out of the domain where these two red lines are and allowing your director to be discontinuous across those two lines, and actually that's fine. It would give you the same energy and the problems are equivalent. But bounded variation problems, they do have some promise in that area, but they do have problems also in that the choice of these cuts that I've made here is incredibly non-unique. So I could have also cut it along there and allow the director to be discontinuous along there. I could have cut it across the middle, or I could have even cut it like that. And actually, that is a valid cut, and I could allow it to be discontinuous along this line, that sort of strange line. But that could perhaps be dealt with if you included an extra term in this minimization to do with the length of the discontinuity set. So that's what I have done, and what I would like to do in more work is actually to show this Q-tensor theory, this uniaxial Q-tensor theory, but with variable S this time, and show this is actually equivalent to the Ericsson theory. So Ericsson allows variable S. I've done enough work on this to convince myself it's true, at least, but there's a lot of technical things to obstacles to be overcome. This is going to be proved. But yeah, so S, I want to be a Sobolev function, and then S times the director to be in this strange SBV space. And one of the things I found most confusing when I started studying liquid crystals was how there are so many different theories as to know which one should be used in which situations. But maybe these three theories, perhaps they are all linked, so depending on the assumptions on your domain omega, and depending on the function space and how you set up your problem, it might actually be how you set up your problem. It seems might be at least as important as all the analysis you do during your problem. And so, in other words, uniaxial Q-tensor theory and Ericsson theory could actually be exactly the same theory in function spaces. Okay, I haven't got a final slide, so thank you for your attention.
Well, we are running perfectly on time, so there's still time for a number of questions.
Sure. two idiotic questions for my education.
Okay.
First, why you define the pitch as 2 pi over p? N and minus n is equivalent. I would define pi over p. And
Oh yeah. Okay. Yes. Yes. I hadn't thought about that particularly because, like you say, when you turn halfway around, I mean that doesn't affect.
absolutely equivalent.
They are equivalent. Yes. I mean, it wouldn't actually. It would just all it would do. I think if I assume that, it would just change the values of these t by a factor of 2. I don't think it would change the
Of course, yeah.
qualitative behaviour. But that's something I hadn't particularly thought of. But you are right. It's just normally written as such.
And equally idiotic question, why you restrict yourself to uniaxial Q? Cholesteric basically biaxial by symmetry.
Well, for the moment, for ease of calculation, I mean, I would love to be able to go to biaxial Q in the future. I mean, where was it? Oh, there it is. Yeah, I would love to be able to. If you have biaxial Q, you have a second term on the end of that one, another S2 m times 0 minus the third I. I would, if this could be shown to be true, then I would then try and go on to the biaxial case and perhaps show it was somehow sort of two Ericsson theories put together. So, but that's just a bit further than my theoretical ability can take me right now, or a lot further. But I would like to.
Question?
Yeah, I had a sort of maybe you just glossed over that for me to follow. You had two cylinders which were touching, and one which were twisting the other way, and the other going the other way, and because of n going to minus n symmetry, but surely you have to match the boundary condition at the surface, right? I mean, there will be a balancing of the director as you go from one to the other.
Yes. What do you mean? So if you have somehow have an array of these, you do have to match the boundary conditions, and that is one of the main problems as to why it's difficult to analytically find some sort of state which includes these. I mean, numerically people do some things with this, but there's very few analytical results with them. I mean, if you have to have the radius exactly right, so that as it's on a radius, I think it's somehow pi over t or something, so that actually the director is tangential in the xy plane around the cylinder, and then you can actually put two next to each other with n to minus n, because they only twist one. You only put them up one way. You turn them. There's something about you can't actually put them the other way up next to each other because that's.
So it's something like, if you think of the curve, one going this way and the other going that way, shouldn't that match basically something like an antiparamagnetic order?
Yes, I mean, yeah. So one comes around, say anti-clockwise. Say they all come around anti-clockwise. Then when you put them together, then you have one point. The lines you intersect, you've got them like this.
But if it's the other way, then it should.
But I think if it's the other way, actually, they have to twist one way. The sign of t tells the cholesteric it has to twist one of the directions. They can't twist both ways at the same time.
Tom?
So I guess I don't understand why you want to look at a theory that has a grad s squared term and not an s minus s naught squared term as well.
So, so s naught being the
preferred value of s.
preferred value, okay. Well, I mean, yeah. I mean, because having a grad s term, it still wants s to be constant. So if you, presumably your boundary conditions would have s being some s naught on the boundary, probably. Presuming your boundary conditions aren't too stressed, if s equals s naught somehow on the boundary, s is still going to want to be s naught throughout the cell. So if you had grad s minus s naught, then
I mean, the system wants to have at least in the uniaxial approximation, a fixed s naught to thermodynamic equilibrium. I don't know what that means.
This can be done by adding some further potential.
yes, I mean, if you had grad s minus s naught, you still have the grad s squared, but you just have a
You have the grad
minus
s squared
naught.
term, but the grad s squared term would say I could set s equal to lambda x, and I would have a lambda squared energy everywhere, and S could grow indefinitely. And the system wouldn't like that.
That's worth it. Yeah, I hadn't ever seen Erickson's theory with a grad S minus S zero, so I hadn't thought about it. But,
Might add a potential,
No,
which is
no.
better,
okay.
and which has a minimum at
No,
that
no,
point.
yeah, I just,
So this is only the elastic term.
Oh, do you mean
That's the point.
the bulk energy term? Oh yes.
This is
Sorry,
the
I
only
always
elastic.
ignore the bulk energy terms at the moment. So yeah.
Any further questions? Well, I have one since there's still a couple of minutes. In the periodic minimization problem with L1 and L2 in general, I wonder whether L1 and L2 are prescribed at the beginning or whether they will emerge out of the minimization itself.
Well, I keep them as free as possible because I don't want to prejudice finding a certain period. But I mean, I haven't as of yet found any analytical two-dimensional state which gives a lower energy value. So it's slightly academic at the moment. But yes, they are essentially variables in the problem as it sounds. They can be adapted. Yeah.
All right. Apparently there is no further questions, so we thank you for